Welcome back to Physics with Miyoshi. Today we're going to talk about a couple specific forces, namely normal force and an application of normal force, which is apparent weight. So what exactly is normal force? Well, normal force is not a normal in terms of everyday kind of force. It is what a normal force is particular to surfaces. So if you have a normal force is usually designated Fn, and a normal force is the component of a force that a surface exerts on an object that it's in contact with it. So the normal force acts perpendicular to the surface. So if I'm standing on the ground exerts a normal force perpendicular to the ground on me. If I'm leaning against the wall exerts a normal force on me perpendicular to the wall. If I set something on a table, the table exerts a normal force on that object. And in this case, as long as the object is not accelerating, well, actually in any case, as long as the object's not accelerating and is in contact with another surface, then that normal force will be exactly opposite and of exact same magnitude as, in this case, the weight. In case of person leaning against the wall, whatever that force is that you exert on the wall is exerting back on you. The ground, again, it would be the ground is exerting a force on me opposite to my weight. And that's just based on Newton's third law, equal and opposite reactive force. And in this case, as long as it's not accelerating, in this case it's standing still, so as long as it's not accelerating, that normal force will be exactly equal to the weight. Now what if I decided I'm going to go ahead and use some force to go up, to pull on this guy, to lift it up? Well, whatever that force is going up now, my force of my normal force will be it'll be the exact same size as the weight minus those two forces, or the lifting force. If I have some forces going the other way, maybe I'm pushing down on it instead, then that normal force will be equal to the weight plus those forces pushing down. And if I have somebody holding up on this weight, just so that it's exactly the weight of the object, in other words, it's not accelerating, but it's not, but I'm holding all the weight with a rope or something like that, then in that case my normal force would be 0. What if I keep, and we could go on and on and on thinking about different types of forces we could put on there, and the normal force will be exactly enough to keep this guy from accelerating, so that the net force is 0 because we have no acceleration. So as long as our net force is 0, the sum of all our forces will be 0, and that's one of the reasons why we think about why normal force is so important. There's going to be important for other things later on, like static friction and kinetic friction, but we'll worry about those, and rolling friction, and we'll worry about those a little bit later on. But when will how long will this normal force continue to exert the same force necessary to keep this guy from accelerating? Well, it's going to keep that same force as long as it's not accelerating. So as soon as it starts accelerating, then the normal force will either go away or something. And in that case, what would happen is, when that would happen would be if I broke the table. If I put so much weight on the table that it finally accelerated, broke through the table and accelerated through there, then my normal force would not be pushing on it anymore. But as long as I have a net force of 0, that surface will continue to exert enough force to keep that guy from accelerating. So, normal force is very important, and we will get back to that later on. And the application of normal force is standing on a scale. And if you stand on a scale just that's not in a place that's not accelerating, then it'll give you your weight. The scale will give you the weight that you truly are. But what if you're in an elevator and we have a big platform scale here? What if we're in an elevator and then you've probably felt the sensation when you go up in an elevator, you feel heavier. When you go down in the elevator, you feel lighter, at least while it's accelerating. Once it gets to a constant speed and not accelerating anymore, then you're back to your normal weight. whether it's going more or less. Well, what is that really doing? Well, if you actually put a scale underneath you, like we have here, and you've got an elevator, and then if as the elevator accelerated upwards, you'd feel heavier, and the apparent weight, the weight on the scale, would actually show that you are heavier. If you were accelerating downwards, then the apparent weight, or the weight on the scale, would actually show that you are lighter, feel lighter than you are. And so if we think about this guy, if we accelerate up, then what we can do is we can actually figure out mathematically what our apparent weight would be. So if we look at it only in the y direction, the sum of all our forces in the y direction is our mass times deceleration, which we know over and over and over again. We've used that. In this case, if I look at the two forces acting on this person here is our normal force, which is the force of the scale pushing upwards, and the weight of the person pointing down. And so those, as long as I'm not accelerating, they're going to be equal, and it'll give you the true weight. But if I'm accelerating, then that's a different story. So the apparent weight is actually going to be your normal force. So whatever that normal force is, whatever the weight on the scale is, that's your normal force. And then if we rate, well, what I did is I just rearranged this equation on this side. So this guy right here, if I rearrange this equation, I get this equation down here. And that's just ma plus mg. Now this mg is in such a way, the m and the g, or the g actually, the acceleration, we're just taking the magnitude of that. Then the direction is taken care of by the net minus sign. So this guy over here will always just be the positive 9.8 or positive 32 feet per second squared, or like I said, 9.8 meters per second squared. But that would be positive. That is your true weight. And this acceleration, if it's positive, I'm going up. If it's negative, I'm going down. And then what you'll see is that the apparent weight, or the normal force, is going to be greater as you go up, which bears that out here, and it's going to be less as you go down. Matter of fact, if you accelerate down, in other words, if you cut this guy off, and I let this guy free fall, then AY would be the opposite of G, so it would be negative G, so then we would have an apparent weight of 0, and that is what free fall is. When you have an apparent weight of 0, then you are in free fall. So think about this. Think about next time you're in an elevator and you have a scale. Go ahead and set it down and step on that scale, and as the elevator goes up, you'll actually see the your weight go up, and as the elevator comes down, you'll see your weight go down. Only for a sec, only for a little while until you stop accelerating, but you will see that change in weight. So, couple of different forces we have. Actually, it's the same force. Apparent weight is really our normal force, but a little more application of Newton's second law, and a little bit of some new force that we have in our lives to calculate a bunch of cool things. So, hope you learned a little bit more about these new forces, and thanks for tuning in, and hopefully see you again for more Physics with Miyoshi.